Okay, good afternoon. So, to resume where we were yesterday, I started talking about kind of different ways the process of inferencing is done, and kind of made the point that much of it is done using this supervised learning paradigm, where basically you have collected data which is labeled with the so-called ground truth, although in reality it is really either a human report or some sort of a gold standard or a reference sensor, which is also collecting. So what you have is a set of labeled data, you train a model, you deploy the model, increasingly right on the edge devices themselves, like your phones and wearables and such, and then output of that is a prediction of a class or a value, which is your regression value. And in particular, a lot of people are now using deep neural networks, which basically a good way to just think about them is a parameterized function approximator built using kind of a repeating unit, which is organized in a very structured manner. And that repeating unit is modeled after the biological neuron, and kind of a first order mathematical model of a biological neuron is that you have a bunch of inputs, you do weighted sum, and then you subject it to some nonlinearity. So it kind of looks like this. And different implementations differ on how you represent the signal and the inputs and outputs, and what kind of nonlinearity you have. And from a purely theoretical perspective, one can show that if you are given such a neuron, then a system composed which has two layers of these, so kind of input feeding into a layer of neuron and then their output feeding into a next layer. And if you have sufficient number of neurons, then you can represent arbitrary mathematical functions. So that's powerful. Across, if you look at the current landscape, there are obviously software implementations of these, in which case these things are just numbers in memory and you're doing multiplications and nonlinear operations. But there are also analog realizations of these, where you basically make use of voltages and currents and such. Usually a problem with analog implementation tends to be that it's very hard to get repeatable things, unlike digital. So that creates a problem. But on the other hand, there are advantages in terms of other attributes like power and such. And then, so there are some pretty large-scale efforts at creating implementations of neural networks which make use of analog technologies or kind of some hybrids. Another class is so-called spiking neurons, which kind of truly seek to mimic the way signals happen in our brain, where essentially it is these things are timing waveforms, and the rate of spikes is what is used to represent the values. And you might recall kind of earlier in the course we talked about pulse width modulation and pulse train, and also it's kind of the same notion that values are being represented in a different manner. Big challenge out here is that how do you train these things? So in a sense, your eventual goal is to find all the thetas associated with every neuron, such that the overall collection is doing the prediction task correctly. When it comes to activation functions, there are a whole bunch of things. So firstly, you can say, okay, maybe let's make it linear. Okay, do you see a problem with that?
Didn't you say it has to be some nonlinear?
Yeah, well, so okay, so linear is a special case of being non-linear, I guess, right? But linear means a summation of linear, so the whole system will be linear, and I'll be limited to linear things. Okay, so that's not terribly useful. Okay, very commonly used are functions which look like these, as in they saturate at some point, and then they have some sort of a intermediate linear region, and yet they are kind of nice differentiable and such. Okay, so they hold nice properties. The problem, though, is that they tend to be computationally hard to implement. Imagine large number of neurons, and if you have to calculate these kind of functions, which typically employ exponents and exponentials and such, so become a problem. So a very common function nowadays, which is used, is a so-called ReLU function, which basically is like a diode, okay, rectifier. That's the rectifying linear something, ReLU. Okay, so basically it is a linear function above 0, and then it saturates down there. Okay, so essentially you get the benefits of the linear, and yet it's simple enough that the training can be done for it, even though it has a discontinuity, it has a kink at the origin. So lots of these different kind of things get explored. It turns out in the analog world, getting these kind of functions is much simpler, because some of our devices already have, if you look at their conductance and all, they already have tan H or some other such dependencies. So realizing these kind of smooth functions tend to be easier in the analog domain, but in the digital domain, you have to implement the corresponding transcendental function. In any case, none of these things correspond exactly to the way the brain works. So the brain does not work by some grand optimization scheme going around learning the ideal parameters. Okay, in case of the brain, at least sort of what neuroscience suggests is that there are there is no separate phase of learning and then inferencing. Okay, so as the neurons see signals, then they kind of reinforce the local neurons, and then the next time around, kind of they do things differently. So kind of the whole thing is bunched together. So while inspired by brain, I mean, they don't really correspond to this. So we'll come back to this in a few more slides, but let's start with perhaps what is the simplest classifier. And again, you would have seen it in some shape and form in some earlier courses, and that is basically the knife Bayes classifier. And its beauty is that it works. Firstly, it's very simple to implement, and the other thing is it actually works pretty well. That is, for a lot of problems, the first cut result from knife Bayes would actually be pretty good, and it doesn't require a whole lot of effort to implement it. So what we have is we have a feature vector of some dimension on a window, okay, and so that's x, and y is the activity level, okay. And now you can think of these things in probabilistic terms. So you can say, look, there must exist some sort of a joint distribution between these x and y, and our good old way of decomposing it. So probability y given x is probability x over y, py divided by px. Okay. Our objective is, I'll give you the x, and you have to tell me the y, which is best in some manner. Okay, and there are many different ways you might think of what best constitutes, but one particular way is that you can say that I want to find the y which maximizes the likelihood py given x. Okay, so so now what really my learning task boils down to is to learn these necessary distributions. In particular, I need to learn probability distribution which connects x, or these are the d dimensions of x, given y. Okay, and so in this case, the parameter is really this distribution. If you think of it as a discrete distribution, then the various probabilities associated over the space of values y and x can take, right? So if y and x were binary, let's say, so I have for each if each dimension of x was binary and y was binary, I'll have sort of probability 0, 0, 0, 1, 1, 0, 1, right? I mean, so I'll have two values kind of defining that. So I need to learn this distribution. The problem that you face is what is referred to as curse of dimensionality, which is as the number of dimensions in my feature space increase, I'm going to require a lot of data to be able to meaningfully estimate this distribution. So this is where in knife Bayes you make a simplifying assumption, which is of conditional independence. So you basically say that probability that I would get x given y is really that I can think of each dimension of x given y, and that they are independent. So I'm able to sort of think of them in this product term. So no, obviously this is not true, particularly if you are careless about the feature selection, but generally speaking, it's not true. All those different features that we listed, they clearly have dependence between them, okay? But we make this assumption, and again, like I said, it turns out in real life, naive Bayes for a lot of problems we encounter works pretty well. So now plugging that back in, probability of y equal to k given the x, plugging that in, we get this kind of equation, right? And in this particular case, now you can say that, look, I really, this is a model I have to learn, right? So that I can compute the probability. So in any given instance, I'm going to be given the x, and then I'll have to plug it in to identify these values for different values of k, given the x vector, different value of k, and so then my predicted y is really the best value of k. So the value of k which maximizes this term. And then since I'm looking at this, so the denominator is the same for everyone, so I can just get rid of the denominator and I can say really I'm looking for the best value of the numerator. So that becomes my task, and in a sense, to be able to compute this, I need to basically get all the relevant parameters of these two distributions, probability of x and y and probability of y. And how do you estimate distributions? Like, how would you go around, let's say I give you a lot of training data, x and y, how would you figure out the underlying probability distribution?
So general distribution.
No, I'm giving you the data. Yeah, that's all.
Actually, it's like have like a sense of like recurrence.
Okay, so firstly, I mean, obviously, first thing you have is that each one of these dimensions will have some alphabet over which they are defined, some binary, value, 10 value, whatever, right? And likewise for y, right? So different dimensions of y will have an underlying vocabulary alphabet for them, and y will have the value. Now my data set would kind of like a CSV file with a whole bunch of rows, each row corresponding to one labeled training vector, right? And that will tell me that in that training vector, I will have values for each dimension of x, and I have the value for y, and I have a whole bunch of such rows. Okay, so let's say I tell you y is binary. So what does the distribution of a binary random variable look like? How many parameters will it have? Just one, right? And I need to estimate that. So what would you do? It's Bernoulli. So you just do a frequency counting, right? Okay. Now, more generally, if I have something which takes, which is not binary but kind of in a higher size thing, you basically repeat the same argument. You have to, right? So, and now to do the conditional one, let's say you have to do probability of, let's say I'm interested in the first dimension of x. The probability of x equals to 1 given a particular value of y. So how many parameters would define that distribution? If it is binary, 2. Okay, if both are binary, right? But in general, given depending upon how many values y can take and how many values x1 can take, you will have more parameters. And how would you go around estimating it? Well, in your data set, you are only going to focus on rows where y is k, and then x is that value out of the total number of things which have y equal to k, right? So you basically are going to count frequencies of occurrence, and that would be a good estimator for being able to do it. So as you can see, that model learning in this case is really kind of counting, it's really a counting problem basically there, right? Nothing terribly fancy kind of going on. So which is what makes naive Bayes pretty attractive, because you can implement it super simply. So learning model parameters in this case really boils down to, so firstly, it turns out that this particular estimator are the so-called maximum likelihood estimators. So for example, to get the value of probability xi equal to vj and y equal to k, you are going to look for all those training samples where xi is equal to vj and y equal to k. So that's equals to this, and the number of data samples with y equal to k. Okay, and then you kind of face a minor little problem, which is So firstly, sort of the reason, if we go back out here, the reason we made this assumption, the naive Bayes makes this assumption, is that if you think about data set, if I were to decompose it this way, then all I care about is probability of xd taking different values. Whereas here, I have to look for entire vectors matching it, right? So if d is very large, let's say d is 100, right? Then I have, and let's say each each xi is binary, right there I have 2 to the power 100 possibilities, and my data set would need to have adequate representation of each one of them for me to be able to learn those things. Whereas if I decompose it this way, then I am basically solving 100 different problems. As long as x1 occurs sometime, different values of x1, different values of x2, and so on and so forth, I will have a lot more samples. So you are breaking the curse of dimensionality by basically employing this independence assumption. So back out here, it may still be possible that I didn't have any sample for some values of some combinations of Vj and k. So what is done there is called smoothing, and kind of the idea is the following, that let's say I were to show you a coin, and you have to estimate the probability it will get in hand. Okay, so what would you do? You conduct experiment. So toss a coin, jot it down. Toss a coin, jot it down, right? And by looking at tails and heads, you are going to develop an estimate over it. But there is also a prior on this thing, right? I mean, you're kind of starting out with some assumption about what it might be, and then these additional experiments are giving you the evidence to refine that prior that you have. So I may start out by saying that, it's a fair coin, but perhaps half probability equal to half. And then as I conduct experiment, each one of them is providing an evidence in favor of a particular, is basically adding to that estimate, right? So over time, I would converge to, if the coin is unfair, to the real value. So something similar happens out here. We start out by saying, let's assume that everything was equally likely. Okay, so we start out with a numerator value of 1, or L more generally, which is some particular value. And then that means in the denominator, if each combination is occurring L times out here, I'll have L times n, I'll have a larger number in the denominator. So it's as if I see things a priori, and so in the absence of any data sample, I will still get some meaningful number. Whereas if I didn't have the data sample and I was definition like this, I would end up with an estimate of 0, okay, or even worse, 0 over 0 is some combination of y equal to k also there. So this is called Laplacian smoothing, where basically we start with a prior, and then the training set is being used as a refinement over that prior, and that thereby we bypass this ugly little problem that if I didn't have data for some combination, I would not be able to meaningfully say anything about it, about the probability value for that particular case. Okay, so so that's a trick that you use. Otherwise, implementing this is really a matter of doing things efficiently, because what you don't want to do is if I have 100 dimensions and each one of them can take some different number of values, and y can take a whole bunch of values, as you can see, there are a whole bunch of different combinations that you need to compute. And by the way, we also have to compute probability for y equal to k also, right? So each one of these. What you want to do is ideally implement it so that in a single pass you can just compute everything. Okay, so it's really trying, because your training data set could be huge, and if you have to fetch it from a hard drive or something, then that's a costly component. So, or even otherwise, even if you're doing it on a edge node or something like that, it could be problematic. So the trick out here is really implementing this counting thing that you are doing kind of efficiently. Other advantages of this approach, as new data come in, you can refine your prior estimates. Okay, if you do things nicely. So this model can kind of update itself. Okay, and you can even do things like which are adaptive, in the sense that at any given point in time, you are going to look at the trained samples that you receive over some time. It could also be that you may realize that once in a while you do some checks and see that your predictions are not coming out right. Maybe it's time to refine the model. So then you kind of go and easily correct data. So naive Bayes' advantage also is that the learning process is computationally easy, although you still have to sort of implement it nicely. Okay. You can also apply it into the cases where instead of features being categorical, they have continuous values. There are a variety of ways you could do these kind of things, but there are generalizations of doing it. So let's look at an example of applying this kind of naive Bayes. So again, perhaps I have sort of different features, different dimensions from the feature vector. So day of the week, time of the day, hours, bathroom sensor count, stuff like that. So I have seven features, and then I may have a whole bunch of feature vectors in my training set. So those are columns up there. And then I could see like what's the probability of attribute x1, which is day of week, which takes values in 1 through 7 for the 7 days, is taking the value 1, given that the activity is personal ID, given that the activity is y equal to 1. So I may need to calculate these kind of things. So the activity label is out here. So px1 equal to 1, given that y equal to 1. So you're going to see which one of these have y equal to 1, and then among those, which one of those has x1 equal to 1. So y equal to 1 we see in 3 places, so that's the denominator, and among those 3, only x vector number 2 has the first row equal to 1, so therefore it's 1 equal to 3. So it's just a counting game going on, very easily implemented on resource constrained devices also as well. Now in this case, I didn't do that smoothing that I talked about. So if we were to do the smoothing, and let's say the smoothing L was 1, then it would be 1 plus 1 out here, and then 3 plus 1 times 3. So it would be 6, so it will become 2 over 6 in this case. It will also do the same thing in this particular case. Okay, so one can do those kind of smoothing, and likewise other things like probability of y equal to 1 you can compute, and probability x1 equal to 1, y equal to 3, and so on and so forth. So your goal would be to estimate all those parameters that one needs to have, and given the data that you can do that pretty easily. Any questions on this? Okay. So next up then, what if I had continuous features? So in that case, as with much of sort of EE, we revert to our friend Gaussian, because this is nice to deal with in these kind of scenarios. So typical approach then becomes that you model probably this conditional distribution as a Gaussian distribution with some parameter values, and then your goal basically becomes to estimate these two values, the mean and the variance. And this can be done again using a similar approach from the training data, except that in this particular case, I'm going to be computing, so the mu is the mean, so you're going to really be calculating the mean value, and the variance again, you're going to be doing it from the data itself. So we do these kind of estimates, again fairly easy to do even for continuous values. So you're going to apply these things. For example, if a feature is temperature reading or height or stuff like that, as opposed to being a categorical stuff. So going back to our example, the energy in the hip accelerometer. So it's this one. Okay, so energy in the hip accelerometer basically refers to that we are going to be computing expected value of x square, where x was reading from the accelerometer in that dimension. So I'm going to get some number, but I would basically go with the Gaussian assumption, and that's a reasonably, again in real life works pretty well. And so mu1 phi is these three values. So we're kind of taking the mean of that, so that's 509, and likewise the sigma. So again, kind of computation just follows directly from the data. Again, relatively trivial to pull off. So these are the way you kind of go around handling both categorical and continuous values features. And then finally, given a test sample, so in this case, let's say I want to tell you that x1 equal to 1, x5 equal to 250, I'm ignoring all the others. You basically now have to compute the forward direction, and so you compute for different values of different possible values of y. So y equal to 1, y equal to 3, and y equal to 2. You sort of compute these things and then see which one yields the largest value. Okay, and that's the predicted value. So yeah, so the math is kind of worked out. So all of this is pretty straightforward. Like I said, it's popular partly because there is some sort of theoretical sort of machinery behind it, but also because it's very simple to implement, and the initial probabilities, those priors, can come from just assuming everything is uniform, but you could also have it coming from some experts and all. Often, particularly for these accelerometer, these kind of data and all, it actually gives pretty decent results. Just starting out really. Okay. Yeah. Now, when it came to continuous attributes, one of the we made the assumption that it was Gaussian. For the discrete, we didn't. For the discrete, we allowed for arbitrary distribution, but for continuous, we just kind of made the assumption that it was Gaussian. And in reality, that assumption often breaks down. So for something like height or these kind of things is probably okay, but imagine other type of attributes like start time of an eating activity and all. Oftentimes these are multimodal. So if you were to think about like what's some feature which is a function of occupancy, how many humans are there. So if you look in a building, there might be kind of different peak points. Maybe there is in a restaurant, there might be a peak at the breakfast time and a peak at lunchtime and a peak at dinner time. So it's not like a Gaussian distribution in this particular case. So we would expect the distribution in general to have kind of multiple such things. So a very common model to handle this case is what is called as a Gaussian mixture model. So we basically say that the phenomenon is a summation of bunch of Gaussians with different means and variation, different means and variances. So, and then I have more parameter to deal with, but kind of roughly speaking, we are still in the world where things are somewhat easily tractable and all. So so that's what it becomes a model, which is we say that these conditional distributions are now a summation of some number of Gaussian functions, and my goal really then becomes of finding all those parameters, and again kind of doable. So more complicated, but still kind of doable. So it turns out that to be able to solve these type of problems efficiently, there are lots of algorithms and all which are around, but kind of iterative algorithms often get used. So they're kind of along the lines of, remember very early on in the scheduling problems, we had encountered fixed point equations, x equal to fx, you're trying to solve those kind of things. It's the same kind of concepts get applied out here, which is you initialize it at something and then you kind of see what estimate they are given, and based upon that you go around and refine them. So sort of instead of solving in a closed form manner, you basically start with a guess and you kind of see how it is doing and then pert up the guess and keep doing it. And these kind of so-called gradient descent, and these kind of algorithms are pretty commonly there. So there are numerically sort of ways to go around doing it. So you start with an initial estimate. So you initialize all the variables of the model with some initial estimate. Then for each data point, you in this particular case, you each sensor reading that you have, you assign it to the nearest component of the Gaussian that exists. Okay, so you kind of assign to that in this phase, and then you are going to update the parameter based upon that. So these kind of algorithms, you also, this is like a clustering problem, right? So we're trying to assign these different readings to those different Gaussian components. So you start by assigning it to one Gaussian or one cluster, and then recompute things based upon that, and then do a reassignment. And you keep doing it until you converge to a certain number of Gaussian parameters. This is very similar to what happens in when clusters are discovered in data, and also you kind of start with k-means. So you start with some assumption and then refine your assumption based upon doing it. So broad category of algorithms which work in this manner is that you make a guess, you see how that guess does, you kind of refine it and sort of converge based upon that. So expectation maximization kind of falls into the same category. Okay, so in a single step, then being able to develop a model independently for different windows, sort of you can apply these and other models. I mean, in some senses, all these models basically you can think along the same lines that if I give you a parameterized model, neural network or otherwise, I can always kind of do this kind of adjustment game, right? That I have to find the best value of the parameters, and I'm going to kind of refine it by iterating things on that. So variety of approaches exist for optimization, generally speaking, for these kind of things. So other common ones, so there is one which is very commonly used is called genetic algorithms. And the genetic algorithms draw their inspiration from the way populations evolve, okay? So what happens in population evolution? Individuals have different strengths, weaknesses, different traits, and then when they mate, the successor has some combination of those, and at any given point in time, some of the individuals have more or perform better and the others not so. So what genetic algorithms do is they kind of start out with a bunch of individuals. Individuals may mean in terms of models, a model with different settings of the parameters. So I can start out with a bunch of them. And then I do the equivalent of them mating. So that often boils down to taking bits and pieces from one and the other. So like for example, one very stupidly trivial way could be that I can create a new model by taking some parameters from one model and some from the other, okay, and then create a new model out of it. So in a neural network, you might imagine that the new neural network may just borrow some from the one and some from the other. The key thing is at every step you prune the population. So you basically, the idea being that the weaker individuals die, and among the good ones, you are going to do this marriage, and you're going to get a large new population again, and you're going to repeat the same game. You're going to assess it, the healthy ones survive, and then you repeat this process. And how you do that sort of combination, the mating process, is where sort of you'll have to decide, one has to decide kind of various types of strategies. So you marry the models and then sort of keep refining them. So that's one example of an optimization strategy. Another one comes from physics. It's called simulated annealing. And so simulated annealing refers to the process by which crystals settle to their crystalline structure. So what does annealing mean? Anyone? Must have seen in physics. Annealing. Come on, no one done physics? Okay, you are the TA, you are not supposed to answer. Okay, so annealing is the process in whatever chemistry, physics, material science, whatnot. You bring the system to a high energy state, so heat it up, and then you let it slowly cool down. Okay, and what happens in that slowly cooling down process is that the original imperfections disappear and the crystalline structure settles into a nice clean state. Okay, so you kind of you make the whole structure better that way. Okay, now what happens at high energy? At high energy, things are able to move around a lot. Okay, and at low energy, they are kind of frozen. So this notion of going to a high temperature with the corresponding high energy is really giving the freedom to move, freedom to try out new things. So what happens is the following. I mean, you have these so-called greedy algorithms, which at any given point in time say, okay, if I were to perturb this model parameter, does it become better? And if so, let me take that step. So that's simply going down the descending down the steepest path. So that's the gradient descent. Okay, so I measure the gradient. I see what is the perturbation caused in my error function. So I'll have some error criterion, right? I mean, given the current model, I feed x, I get a label, I get a prediction, and I have a true value because I have the training set. And then I take an error from that, and then I say, if I were to perturb the model parameter, then what happens to the error? And I'm looking for the perturbation which will reduce the error the most, right? So I'm going to find out what change I should do to the model parameters such that my error reduces the most. So I'm looking at the gradient or derivative of error with respect to your model parameters, and then I take a step in that direction. The problem though is that your landscape is fixed, right? So if you are wherever you are, you can get down to the nearest sort of valley point, but you're going to be stuck there. So whereas a real deep valley may be somewhere else. So what simulated annealing does is it basically, by raising the temperature, it basically lets you do things where you can make longer jumps. So instead of taking a small step down the descent, you can take huge steps. So you can move around the landscape, and then as you gradually kind of cool it down, things settle to a better structure in physics, and I guess in this case you end up discovering hopefully better optimum. So that's another example. But most common one are simply the greedy descent kind of thing. You just take the step in the obvious direction, okay, and then so that's gradient descent. How many of you have heard the term stochastic gradient descent? Okay, 1, 2, 3, 4. You're taking course, right? Akash, you're into what is stochastic gradient descent?
I think
Right.
it's like gradient descent.
Well, it is
Yeah.
like gradient descent, yeah. And anyone else wants to take a stab?
Well,
So what's the difference between gradient descent and stochastic gradient descent?
At least in the context of neural networks, like you use like part of your data, like chosen like randomly, and then like you like go down to.
I think in SGD
That's-
you perform
okay.
it in a small
How many of you are
vacuum.
doing Professor Jonathan Gauss course? Okay, many of you. Has he talked about stochastic gradient descent?
Yeah.
He has, okay.
It's between a fixed step size and
No. So step size is related to the learning rate,
Yeah.
right? Small step size, you are taking cautious steps because if you take long step size, then you may overshoot and all, right? So step size affects the learning rate, and it may cause variety of issues. So step size control is very important, but stochastic gradient descent is doing something else, which is important.
Technique estimates gradient based on the current sample.
Right.
Yeah.
So remember, to do that gradient descent, I need to have the gradient.
Yeah.
Okay, and how do you get the gradient? Well, one way to get the gradient is to compute for all values in my training set and then compute the gradient. But then that requires me to fetch everything. Okay, So that becomes quite problematic because these are huge data sets. So then the notion becomes you basically compute, you estimate the gradient. Okay, that's why it's called stochastic. And you estimate the gradient by doing it on a subset of the training samples. Okay, and then the set of the subset that you estimate it over, what is it? What's that called?
Oh, batch.
Batch size, right? Okay, so small batch size. You compute. Oftentimes, batch sizes are what? What kind of batch sizes are you?
Like we use like 100, 200, like.
Okay, oftentimes even as small as like 8 or 16 or something. Okay, but the idea is very small batch sizes. You estimate the gradient over it, and then you keep applying these things instead of fetching the whole data, computing the gradient over it. Now, these concepts, gradient descent, stochastic gradient descent, and all, they are nothing specific to neural networks. It's just a strategy for optimization. It's just that in neural networks, we also began to face tremendous amounts of data, and that is why it became imperative to do it. I mean, if you have a small amount of data, you don't have to deal with it. I guess like poor Akash and Nat, who's not here today, these guys are dealing with training data sets and all, which are what, 40 gigabyte or something? 100 gigabyte, right? Okay. So very soon you hit these things, not mega, giga. Okay. So very soon you begin to hit these things where you can't really fit stuff into the memory, right? I mean, and then fetching things off, on and off the disk, even a flash drive can be pretty problematic. So a lot of effort goes into optimizing these things, and with sensor data. So some projects with smartphone data and all that I've been a part of, we have dealt with data sites which are like half a petabytes. How much is a petabyte? Anyone?
Oh, it isn't like
500 terabytes.
500 terabytes, exactly. Yeah. So basically a huge amount of data.
How do you get to 500 terabytes?
By having 800 users from whom you are collecting data continuously over 2 or 3 months, at reasonably high rates. Okay, so you get to it, and you can only imagine what kind of data rates bigger companies have to deal with, right? I mean, particularly as things like mobile health and all come into play, where you are kind of making inferences, and also like imagine like I read that for developing its EKG sensor on the Apple Watch, Apple had a cohort of 100,000 individuals. Okay, so just imagine the kind of data they had collected and all to develop that one model. Okay, so it's a very expensive process, this whole model building, and getting it right and appropriately validating it and all is very important. Now, I think some of you are very brave and are trying to use awful sensors like Hexaware, where they are just population of 2 and 3 individuals, and so that's quite brave. But obviously, real life is not going to be anything like that. Okay, you'll have a lot more users and a lot more data, and also you can't just train these things on your laptop or even a machine with one or two GPUs. You kind of run it on big clusters and stuff like that. But long story short, this is an example of the same category of models. Okay, then this assumption that windows are independent often breaks down, and therefore in that case you need to really learn a model over sequences, okay, as opposed to each window at a time. And there are a variety of ways of going around doing it, but one common model is something that I've shown previously also, which is there is this hidden state, and then the observations are being done over that hidden state. So I have this underlying system is moving from state to state, and then I am observing not the state, but really a sensor reading over that state. So the idea here is that while I'm in a given state, my sensors are going to report some value. Then when I move to a different state, my sensors are going to report a different value. For example, let's say trivially speaking, if there was a sensor measuring how far away from the ground my head was, okay, then if I was sitting versus standing up, that height, how high my head was above the ground is going to differ, and then probably, given the natural errors of the sensors and all, you could very reasonably say that maybe the reading is going to be a Gaussian because there are errors. So I could say there is a Gaussian but the parameters of the Gaussian depend upon the state. Okay, so conditioned upon the state is a Gaussian with a particular value, but the state gets to decide what that is. So again, you can model this thing as in terms of conditional probabilities and all with the associated parameters. And then the problem boils down to is trying to identify what those parameters are. One of the assumptions that is made is, and the reason the name hidden Markov model is that the underlying state states are assumed to be connected by the Markovian property, which is basically saying that the given let's see, given the current state, the next state is independent of the prior states. Okay, so given the state at time t, the state at time t plus 1 is independent of the states which came before t. Okay, so essentially the state at t is capturing everything useful about the history. So that's the Markovian property. So it turns out that these things can be solved very efficiently using dynamic programming type approaches. It's called Viterbi algorithm. A little tidbit of history. Viterbi algorithm was done at UCLA. So yesterday you were talking about what came out of UCLA. This too. Okay. Probability. So you compute these things. Again, these are all this parameter. All these things are parameter estimation things, and for some cases you have efficient algorithms. Other cases you sort of just don't. Decision tree, very powerful, very common, and what I have encountered in my own kind of doodling with machine learning stuff and all is that other than neural nets, it usually gives the best results. Okay, I mean time after time I've encountered that for the kind of sensory problems and all, it actually works pretty well. And there are variants of these where they're called random forests, for example, where you actually have a whole bunch of trees and different trees, and they're kind of dealing with you have an ensemble there. But kind of an intuitive idea, is the name kind of implies, is that you create this kind of a tree-like structure where at each node you evaluate some predicate, and then based upon that you take one branch or the other. Okay, and you can imagine many different ways of doing it, but I've just shown an example out here. What's the count on the bathroom sensor, and then depending upon that, what time of the day it is, and then you come up with rules like, okay, maybe whatever, what kind of event might be happening. The advantage of decision tree is that oftentimes you can also incorporate expert input easily. I mean, if you talk to in some domains, when you talk to I don't know, medical domain, talk to the doctors, they might say, if the ECG peak is this but not that, then a heart attack is happening or stuff like that. They have these sort of rules and all. Okay, and they're very easy to incorporate. One of the challenge in machine learning models often is that how do you combine these two different sources of information that exist, the human input with what the data is telling you, and things like decision tree kind of help in that regard also. And then another very popular model, by the way, I'll show you examples of these. Well, perhaps, okay, I'm already over time, so but let me just wrap this one up, and then I'll finish it on next Friday. So support vector machine is basically kind of the notion out here is that I have to find a decision boundary. So you can think of it like I'm trying to figure out a hyperplane such that things on one side are in one class, things on the other side are in another class. And what it seeks to do is that it seeks to identify a good plane, and the good plane is defined in terms of the distance of the nearest objects on either side that exist to it. Okay. And so the search problem out here is you're trying to find the parameters of those planes, and you're trying to find a set of planes which are collectively going to divide my training set into the requisite labels. So, and then of course there might be things on one side or the other. So it's a generalization of a linear classifier, like the best fit straight line, linear regressor. It's kind of a generalization of that. And one of the things which makes it particularly powerful is that while it may be the case that my data, like in these cases, the example is sort of a clearly visible line which is dividing. But let's imagine something like data is clustered with a circle, and then the other category is kind of an annular, what is it called, annulus around it, right? I mean, so a circle in the middle and then kind of an outer thing surrounding it. In that case, I cannot find a line, but if I were to map the data into a different space, then I can make it linearly separable. So what makes SVM powerful is, I mean, in that case, you'll do a polar coordinate type transformation. Okay, so if you can apply a nonlinear kernel, as it's called, but basically I can apply a function to the input data, then I can map it to a space where the categories are linearly separable, and then I can apply SVM to that. So support vector machine with nonlinear kernels kind of do that. So you basically feed them various kind of kernels, and in an attempt to make them separable, so you're trying to essentially project them into a different space where SVM can be applied. Okay, so that's the idea behind SVM, and again, kind of very powerful. Now, these things are, I mean, there are excellent libraries and all for sort of doing these kind of things, and there are packages. Perhaps the most famous one which everyone uses is something called scikit out in Python, but they're available in MATLAB, and there are entire sort of other specialized packages around this. So it's very easily accessible. It's a different story implementing these things on a resource constrained device, but even those have begun to appear. So ARM, for example, has released a machine learning library where kind of you have these things. Apple, Google, they all provide it for the smartphone. So a lot of the standard stuff, which previously used to be just playing in Python or MATLAB and all, you can easily, once you have the model, you can sort of run it out on these devices also. So SVM, decision tree, knife base, they collectively provide a pretty reasonable set of things for non-neural network-based ways of analyzing sensor data, and often pretty effective. Okay, in fact, sort of you should resist the temptation of running to neural networks as the answer. Why?
They're really like resource heavy.
Okay, let's say I give you tons of, let's say I give you gazillion GPUs, will you still apply it?
Maybe.
Okay, so he'll apply it. Anyone think what else distinguishes neural networks from these classes of models?
Not necessarily very explainable.
Okay, that's a great point.
Yeah.
So what Tyler is bringing out is the thing that neural networks are kind of black magic. Here we get decision trees and boundaries and all, and you could apply some meaning to them and in an attempt to explain it. So excellent point, although that wasn't what I was looking for. Let's say I don't care about explainability.
Yeah.
So neural networks have a lot more parameters.
Yeah.
Right?
They're hard
To
tell.
be able to train lots of parameters, what do you need? Lots of data. And if you don't have lots of data, then and you still train a neural network, what will happen?
Crap.
Huh?
Crap.
It's crap
Why?
because it doesn't.
Parameters are like.
Yeah, it's overfitting. It has too many parameters, so it just memorizes your training set,
Yeah.
right? So essentially it becomes like a lookup table because it has way too many parameters. It'll just memorize the thing. And that's not what you want, because then it will do very well on that training set but will do awful otherwise. So if you don't have too much data, then you should use the simpler models. Your model parameters should, the size of the parameter set should be well matched to the amount of data you have. Otherwise, you will end up into this overfitting kind of situation, and that's not good. So particularly, again, if in your project you are doing any sort of ML, it's unlikely you will have enough data, and therefore, unless the purpose of your project is to evaluate neural network implementation or something like that, other than that, you should consider using these simpler models because they have lower model dimensionality, fewer parameters, and therefore you would actually do better. Okay. Much of the gains of neural networks are because of large amounts of data, and you take that away, then you're basically creating a gigantic, expensive lookup table, basically.
Yeah.
Okay, so you don't want that.
Just a quick point, yeah, if you have like a linear regressor and you give it 2 data points, then it's the perfect length of those 2 data points.
Absolutely, but then that's the only thing that it will classify. So if the,
Yeah.
so great point. Okay, so there are thumb rules about like how much data you need given the size of the number of parameters and stuff like that. So again, some of your ML courses might cover this, but from a practical perspective, the takeaway for you, have things well matched. Okay, don't just go after the fashionable neural networks or a complicated model if you don't have the data. Okay, so see you guys, and please come for the Thursday lecture. Otherwise, my postdoc would be mighty disappointed. And I think he's the only one talking about security, which I think is pretty important. So come. He actually is going to show some interesting ways of breaking into software.
Yay,
Okay.
hacking.
Yeah, hacking, exactly.